In this mini lecture, I'm going to talk about finding the area between two curves. Now, we've already talked about finding the area just under a curve, which by that we meant the area below the curve but above the x-axis. Here we're going to talk about finding the area of a region bounded by two or more curves. Also, sort of as a note, a curve in mathematics does not necessarily have to be curved. A straight line is also considered a curve. For our purposes, we'll say a curve is just a graph of a continuous function. There's a more technical mathematical definition than that, but for our purposes that's just fine. So any continuous graph of a function, no gaps or anything, and we're going to be fine. So here's an example of a region S down here. It's between two curves. We've got y equals f of x, that's sort of this pink curve on the top, y equals g of x on the bottom, and we've got these vertical lines x equals a and x equals b. And we've got these functions are continuous, and for our purposes again here, one of the curves, in this case f of x, is always above the other curve, g of x. And so that's what we've got written out here. And so that's what this region S would be, right? It's all points x, y such that x has to be between a and b, and my y coordinate has to be between the bottom y coordinate, which is g of x, and the top y coordinate, which is f of x. To find this area, we're going to take this interval from a to b and divide it into smaller subintervals, like we did when we were doing area earlier. And we're going to form a rectangle for each subinterval that covers the distance from g of x on the bottom to f of x on the top. Then we're going to add up the areas of all these rectangles. So here's this as a typical rectangle. I'd have this delta x here, that would be the width. The length, well, that's a change in y, right? What we've got here, this length is a change in y. So that's going to be the y coordinate on the top minus the y coordinate on the bottom. The y coordinate on the top is f of x. The y coordinate on the bottom is g of x. So that's where we take f of xi star minus g of xi star. Remember, xi star is just some x coordinate. It's that sample point that's somewhere in this subinterval. And I take f would be the y coordinate on the top, g would be the y coordinate on the bottom. And to find that total length, I would just subtract top minus bottom. What we do then is we do that for a bunch of rectangles, and we add together all of those rectangles to approximate this area. Then we'd let the number of subintervals approach infinity. When this happens, the sum of the areas will become a better and better approximation of the true area between the curves. So remember, this delta x, that was the width of one of those subintervals. This was the length, the y coordinate on the top minus the y coordinate on the bottom, right? Y top minus y bottom. So this whole thing here, area of a rectangle, but then we let I go from 1 to n. So we do the first rectangle, then the second rectangle, then the third rectangle up to the nth rectangle, but then we let n go to infinity. Well, this is a limit of a Riemann sum. That's what we've talked about earlier. That's just the definition of the definite integral. So we really can define this area that we're trying to find, the area of S. It's just going to be the integral from a to b of just f of x minus g of x dx, right? That's where the f of x minus g of x comes from, and the delta x is my dx. So this is my length, this is my width. Now, to be sure all areas are positive, remember we had negative areas if we were underneath, say, the x-axis. We must always be sure that we're integrating from the bottom curve to the top curve at all times. If the curves cross, we'll need to break the integral into separate parts, not necessarily two. Here we had to do 3, so that's into separate parts. We don't need that word 2 there. Let me just cross out. So 2, we don't need that. All right. So as an example here, we've got this red curve f of x. It starts out on top, but then it goes down below g of x and then back up on top. So which one's on top and bottom switches at this point C and at this point D. So if I want to find the total area, all three of these areas added up, when I go from A to C, I'm going to have to go from bottom to top. Well, as I go from C, then I have to take we have to take the top curve minus the bottom curve. Okay, so we have to take top minus bottom. And so in this range here, my top is the pink curve f of x, and my bottom is the blue curve g of x. So that's what I've got here, right? That's my top, that's my bottom. But when I go between C and D, now my bottom is f and my top is g. So g now becomes the top, f becomes the bottom. And when I go to this third part from D to B, well, now I'm back to f being on top and g being on the bottom. So top minus bottom. So you just have to be careful of that. You have to look at the picture and decide, what am I going to have to do to take top minus bottom? Finally, there are some situations where it's more helpful to consider curves defined with x as a function of y instead of the usual y as a function of x. So this type of area here, the problem would be if I try to draw in rectangles that are vertical, I draw in a vertical rectangle here. The problem is it's not going between the two functions. It's starting on g and it's ending on g. And that's just not going to work. So we don't want to set it up that way. We don't want to try to set up vertical rectangles. We're going to set up horizontal rectangles that go across. In this case then, to find this length that might be here, we could say that that is a length delta x. Well, to find a change in x, I have to take the x-coordinate on the right minus the x-coordinate on the left. Right? To find change, I always subtract. I'm going to take the larger x-coordinate minus the smaller x-coordinate. But this is my x sub right, this is my x sub left. So I would take f of y minus g of y, and that's exactly what we have down here. So again, make sure for this type of region you're always subtracting the left function from the right function.